Everything works. You are live now, all of you. Okay, good morning, good afternoon. Thank you very much for joining us today, Georgi. Georgi is a special guest because we know each other very long time, and I'm very looking much forward to your lecture. I would like to introduce you shortly. Please add if I miss something. So Georgi Petrov is a practicing architect and structural engineer. He's associate director in the structures group at the New York office of SOM, Skidmore, Owings and Merrill, where he works on high rises, long span roofs, and specialty glass and steel structures. The projects are placed in North America, Asia, and Middle East. He has been, for example, a lead engineer for the 300-meter tall One Manhattan West Tower and the 400-meter tall Shenzhen Shum Tower 1 in Shenzhen, China, which features a ladder core, brand new structural system for super tall skyscrapers. In addition, Georgi Petrov is a leader in pioneering SOM's involvement into design for structures in outer space and in developing novel project delivery methods, which he does in close collaboration with fabricators. He is a licensed architect and a professional engineer. He is also a teacher, so he teaches at the New York University School of Engineering. And together, Georgi and me, we have the pleasure to chair a session on space architecture, the ICES, which will take place, the next one in 2021. If anybody of you would like to submit a paper, you're welcome. The floor is yours, Georgi. Thank you for joining.
Good morning and good afternoon, everybody. Thank you very much, Sandra. Yeah, it's been a pleasure working with Sandra. We've been hosting the space architecture session for 5 years now, I think. And the funnest one was when we actually came, we had it in Vienna, and we had a symposium that we organized, Sandra and I, at TU Vienna. That was a lot of fun and very cool. So today, as Sandra said, I'll talk about both architecture and structures. So most of my education is in architecture, but I'm working as a structural engineer. So there's a lot of construction and structures in my talk. I will talk, I think the original title was Innovative Design in Tall Buildings, but I'll cover a little bit of history, and there'll be a lot of sort of themes that repeat through a number of projects. But I always like to start with the really big picture and just to set the tone. I don't know how many of you recognize this. This is a picture of the Earth from the edge of the solar system as the Voyager spacecraft was leaving past Neptune. It turned around. And just as a reminder that we live on this beautiful small planet, but on the cosmic perspective, we're just a little dot in this big universe, and it's the only home we have. And there's a lot of us. This is a graph of the population, human population, and currently I just looked it up yesterday, we're about 7.5 billion. And depending on how you do projections, in the next 25 years, there will be between 2 to 3 more billion people on Earth. And we, you guys, and still me, I guess, all of us architects and engineers are going to have to come up with buildings for all these 3 billion people. So there'll be a lot of work for architects in the next 25 years, but how we build, these 3 billion people are going to need places to live, places to work, places to play, is going to have a big effect on the future, how we construct all this. And can we have more of what's on the left here, or are we going to do more of these things on the right, which I don't think are the way to go. And the trend is that a lot of us are living in cities. We passed quite a while ago that 50% of the population of the Earth lives in cities. And in the next 25 years, I think the estimates are that almost 3/4 of us would live in cities. And at SOM, we kind of approach this structure, this challenge through the combination of architecture and engineering. And even at the very, very beginning, our firm was founded in 1935. These are the three dudes, Skidmore, Owings, and Merrill. They're all dead now, but Merrill was a structural engineer. So this collaboration between architects and engineers is in the very essence of our practice. And even to this day, we always go out together and design as architects and engineers together. It's not like our engineers doodle something goofy and then give it to the engineers and say figure it out. Especially on challenging projects like tall buildings, we always come up with ideas together at the very beginning. We have a number of offices. The major ones are in New York, Chicago, and San Francisco, but a pretty big office we have in London as well, and then several other cities around the world. And we do a lot of various projects, very commercial renovations, but we're mostly known for our super tall towers. And this is a little bit outdated. This is a lineup of the tallest buildings in the world. At any one point in the at least the last 50 years, a fair big number of them, the red ones marked here, are done and architected and engineered by us. And not only do we design them, but this is sort of a lineup that we have of the structural system for tall buildings and what's appropriate, right? What the structural system that's appropriate for a 40-story building is very different than a structural system that's appropriate for a 100-story building. And these are the different structural ideas and systems for tall buildings. And we have done the very first example of each one of them. So not only we design tall buildings, but we design very innovative and pioneering tall buildings. And I'll show almost all of these to you throughout the lecture. And the other sort of theme that repeats through all the project is that this multidisciplinary approach, but it evolves through technology. And we're not married to any one type of design tool, and we keep looking through the newest. And we've been sort of pioneers also in digital design, going all the way back to the 60s. In the 80s, in fact, partnering with IBM, we developed the first sort of BIM software. Unfortunately, it was Unix based, so it didn't quite survive. It got beaten by AutoCAD in the early 90s. But as new tools come up, we always adapt and change the uses. The last sort of decade has been largely dominated by Grasshopper and Rhino as the main sort of tool where we come up with ideas and model geometry. And very often we find that the commercial tool doesn't exist, so we also write a lot of our codes. So these are a lot of these internal sort of form finding and parametric modeling tools that we have. And the type of thought process is always that you start with some kind of blank slate, a domain where you want to create geometry. And first we come up with what is the correct topology, how are the things connected, both architecturally and structurally. Then we optimize the shape, and only at the end do we make size the individual members. So this is, instead of just drawing some random blob that Rhino allows you to do, and then trying to shove some structure on it, our process is sort of more thorough and more step-by-step, making sure that we have the correct geometry first before trying to make it work, both architecturally and structurally. And then, of course, when you build tall buildings, you need to work with a developer, and they are looking for very specific things. There's a lot of competition for office buildings and for residential buildings. They're looking for the tallest, the grandest, the best spatial experience. Everybody wants big column-free interiors. And in today's world, everybody wants it built immediately. So these are the pressures from the developer and from the constructor side. And then in the last 20 years, the computer technology and digital design has allowed us to be able to draw any sort of shapes. And very often the question is, what is the correct shape? And just because you can draw something goofy and globally on the screen, is that really what you should build? Is that the correct shape? And is that the best thing for the project and for the planet? And so in engineering super talls, this is a sort of a little analogy. I don't know if you've heard of this Hambley's paradox. Basically, if you have 2 stools and one has 3 legs and the one has 4 legs, which is more structurally efficient, which will have less material? And how do you design the legs? Well, the 3-legged stool sits firmly on the ground and it's statically determinate. I don't know if you've taken statics, but basically at any position you put this 3-legged stool, you always know what the force in each of the legs are. You can design it for 1/3 of the things. On the 4-legged stool, though, is statically indeterminate, which means that how the forces in the 4-legged stool are depends on where you put it. And if you put it in a computer floor that everything is mathematically exact, then you can get 1/4 of the force in each of the legs. But in the real world, you never have this. Every floor is sort of imperfect, and everybody knows, sitting at a restaurant table and it like all shakes and you have to shim it and things like that. So the 4-legged stool is always, the force is coming down on 2 of the legs, but as you rock it back and forth, there's a position, where the 2 other legs are always in the air. So you really have to design each of the legs of the 4-legged stool for 1/2 of the force instead of 1/4 of the force. So in a 3-legged stool, each leg is designed for 1/3 of the force, while the 4-legged stool has to be designed for 1/2 of the force. And that's really to illustrate you that for 99% of the buildings that we do, you can just open the code, Euro code, and just follow it, and you'll get it. But for super tall buildings, usually you can't really take the code. It's really about analyzing how the building actually performs, just like the 4-legged stool. It's not what you would think if you just do some math, but think about how it actually behaves in the real world. And so we do a lot more sophisticated analysis for super tall towers than for just typical 2 to 3-story buildings where anything can be made to work. And finally, again, in the setup, what are the other effects on design of tall buildings? So one is zoning. And I'll give here an example in New York, but it's true in most cities around the world. The zoning or the urban planning rules are really govern a lot of what buildings look like. So this is a building in downtown Manhattan in one of the earlier skyscrapers, and it was the first skyscraper that took the whole lot from street to street to street, and they went straight up. And when this building went up, everybody got really scared that we need to make sure that we control what the buildings are, that the sun would be blocked out, and the whole city built of these buildings would really be not a really nice space. And so the very first zoning rule got passed in 1916 in New York here, where they set all sorts of rules that from the street, you can only go up so high, and then you have to start stepping back, and that there's a limit of how far you could go. And then they left this possibility that in the middle of the 25% of the block, you could go up infinitely. So the outline is this building that was built, and then the diagram is what would any future buildings would have to follow. So this has a big effect on what tall buildings look like, and especially in New York City. And then this is a famous drawing by this artist called Hugh Ferris that kind of took the zoning envelope and sketched what it actually means in architecture. And that's why if you look at all the old classic New York skyscrapers, they all look like these wedding cake things. And it's a direct reflection of the urban planning law that shapes the architecture. And the Empire State Building and the Chrysler Building all look this way. The next sort of big influence is this building by Mies van der Rohe, the Seagram building. And what they did with the company is they decided to just take the 25% and build straight up, and then leave the rest of the lot unbuilt. So this is a private plaza in front that's open to the street, and the city really liked that. And so they came up with this, changed the rules to actually encourage people to build this. So if somebody wanted to build another building and leave a plaza like this, they would actually be able to build a bigger building on this lot. And so in the 60s, in the 70s, New York started getting a lot of these boxy glass towers, like the original Trade Center and so on. And that's, again, a reflection of the zoning. And nowadays we have all, there's almost nothing left, no land left to build. And so we're starting to get these really thin towers, especially down south of Central Park. That is, again, a change in the rules of how much you could buy the air rights of your neighbors and build these really skinny, super tall towers. The other effect on tall buildings is program. What is the building made out of? So an office building wants to have big lease spans. In an office building, you can be far away from the window, but people like these big open spaces. In a residential building, in everybody's home, every room has to have a window, right? So there's a limit on how wide the building is. Nobody wants to have a bedroom without a window. So the program that you have shapes the building as well. And if you want to, stack the two on top of them, so very often we do mixed use, where there's some office at the bottom and a hotel or a residential at the top. Usually we put the residential and the hotel on top and shape the building so it steps in or slopes in or curves in. So that's, again, a reflection of the program. So that's another force driving the design of tall buildings. Another one is conveying. You got to get the people up and down the building and all the water and all the mechanical systems. And here, up to 40 stories, everything is quite conventional. When you get taller and taller, above 60 stories, you really have to rethink all of these systems, the elevatoring, the water supply and the air supply. And very often, these are bunched in the middle. So this is like a typical office building. And within the perimeter, you have all the occupied space, and there's all this area in the middle where you try to bunch up all this stuff. This is another one again. This is the Petronas Towers in Kuala Lumpur. They used to be the world's tallest building in the 90s. And so in a super tall building, this core in the middle becomes a big 3D puzzle. And it's pretty challenging that's one of the biggest challenges in designing tall buildings. So you have to put all these things in with sometimes competing pressures. So there's all the structure goes in, and then usually it's a big puzzle to get the elevators right. They drive a lot of the design of a tall building. And in a very tall building, you usually have different zones. So when you come in, you usually have sort of an express elevator to a sky lobby, and then you switch to sort of locals. And the cool thing of this is that you could stack the locals elevators on top of each other in the same vertical space. You have to have a few stories in between for the pits and the machine rooms, but that saves a lot of space. And so you can think of a very tall building as sort of a neighborhood. You have the subway, the tram gets you to the local thing, your local stop, and then you have to kind of walk or bike the rest of it to your destination. And then usually there's some firemen's lifts, and typically people put like restaurants and observation decks at the top. So there's some express ones. And so in a typical one, that you'd have the express, the shuttle elevators, and then you would have the locals. And then usually on every floor, you need some air handling units, depends on the type of systems you use. You usually need some electrical and IT closets, and they all have requirements of how far apart they have to be and where their shafts are. There's usually some plumbing rooms and plumbing chases. And then depending on the code and which country you're in, you have 2 to 3 emergency fire stairs, and usually 1 or 2 fire lifts that only the firemen use in an emergency. And so in each floor, all this stuff needs to make it out of the core. And so that's if you ever work as an architect or a structural engineer in a tall building, it's really a big challenge trying to work this in 3 dimensions. And then finally, obviously, it's a structure. And in a structure for a tall building, we have really 3 forces. There's the wind blowing, there's seismic, the earth shaking it, and gravity. And in a tall building, there's this phenomenon that happens both in a small teacup, but it also happens on the big scale. This is an island in the sea. Is that when wind or water goes past the stationary object, it starts to flow on either side of it in alternating eddies. So we call this vortex shedding. It sheds these vortices on either side of it. And it actually happens. This is the John Hancock with the cloud going behind it. And so the interesting thing is that as these vortices happen, they start shaking the building in a rhythm. And if the rhythm in which these vortices shed matches the fundamental vibration period of the building, then you have big trouble, just like a kid on a swing, right? You give a little push at the right time, and then you could really amplify it. And the thing is that a very tall building, as these vortices shed on either side of it, the building actually shakes perpendicular to the wind. So as the wind is blowing, the building is actually shaking the other direction, and these vortices are shedding. So, the worst thing you can have is a straight building. Can you see the animation here? Is it showing on because it doesn't usually work on very well on Zoom. But anyway, if you just have a straight building up and down, this is a little desktop wind tunnel that one of my colleagues built in their house, and so to demonstrate this. But anything you can do along the height of the building, so to make it that at different heights, the vortices shed in a different period actually helps a lot. We call it confusing the wind. You don't want to get a chance of the wind to get organized and these vortices to shed the whole length of your building. So if you sort of add some notches, that helps a lot. You can also, chamfer the corners. That helps a little bit less. You can do square cut the corners. And the one thing that helps a lot is actually shaping the building. So giving a taper or some kind of a lean to the building helps tremendously. Oops, did this crash? No, okay, anyway. You should be seeing all of them shaking, but I'm not sure it's working. Oh, no, this one. So here's all of them compared. Anyway, so the main force in a tall building is actually wind. The gravity doesn't really control very much other than typical floors. And you can think of a tall building as sort of a cantilever beam. So you have a typical cantilever beam that you have a force on it. A tall building is basically everything rotated 90 degrees. So it's a really tall cantilever sticking out of the ground. And in almost all places in the world, it's the wind forces are more important than the seismic forces. There's very few places like Mexico City and Indonesia and sometimes in Tokyo, seismic forces govern. But you can really think of a tall building as governed by wind. Definitely almost anywhere in Europe, wind would be the governing force on it. And so if you think of a tall building as a cantilever sticking out of the ground, you can just think of it as a big beam, right? We have a beam, we have flanges and a web, and the flanges are ones that support the bending, and the webs is what supports the shear. And so your sort of goal is to put the material to support your tall building as far away from the center, just like you would do on a beam. Or think of it another way. If you're just standing straight with your feet together and somebody pushes you, right? First thing you want to do is spread your feet apart to get a wider stance. So it's the same thing for a tall building. And going back a little bit of history before we get to the new ones, all of these original tall buildings in the US especially, these are the Woolworth building. This is the one where our offices used to be located until last month, Empire State Building. They're all basically a steel moment frame, which means that it's the same structural system that you would build a two-story house, just kind of brought up. And you have the same sized columns basically uniformly spread throughout the floor. So this is the Empire State Building under construction and its floor plan. And think about it, that's not very efficient. You kind of want these columns in the middle are not doing all that much. Just like when you're standing with your feet together, you're not resisting the load very efficiently. And so the story of the modern skyscraper really, I think, begins after World War II. And then it's these two guys. This is Fazlur Khan. He was a Bangladeshi engineer that went to the University of Illinois and worked in our Chicago office. And the other dude is, his name is Bruce Graham. He was one of the leading designers at SOM. And the two of them together, working on several buildings, really came up with a lot of these ideas that we talked about, how to support a tall building. So if you think of a tall building as a beam sticking out of the ground, you really want to put all the materials on the perimeter, basically make a big hollow tube. Obviously, that's not a very good building. It's a chimney. So, so the question is, how do you shape the facade to make it nice and put all of the all of the structural material to the perimeter? He was actually on the Google Doodle a couple of years ago for his birthday. So we made it there. But here are three of the very earliest skyscrapers. If you noticed, all of the buildings around them when they were constructed are these, 20s and 30s Gothic-looking skyscrapers. And here, everything that you see on the facade is a structural element. So this is every vertical is a column and every horizontal is a beam. So this is this idea of putting all of the structural stuff on the perimeter. And then if you look at the floor plans, this is a residential building and the other two are offices. There is no columns in the middle. There's still some gravity columns holding the elevators and stuff like that. But really all of the lateral system, all of the material resisting the wind loads is on the perimeter. And that really frees the plan on the inside to be free of columns. So this is something that's very common these days. That's what you would expect, but these are the first buildings to be able to be really tall and do this. And again, what you see on the facade, the structure is the architecture. And this sort of culminated in the John Hancock Center in Chicago. And this is disclaimer, this is my favorite SOM building. Here, instead of putting all of the columns closely spaced like this, if you do the big X's, you could have the columns spaced far apart. And this kind of combines all of these themes that I've introduced to you here together for the first time. So the developer came with this idea to do two buildings. One is an office building that's kind of wide, right, to make the office work, and then a residential building that's kind of narrow, taking up a big chunk of the ground. And so what SOM proposed is, why don't we take the two, stack them on top of each other. The building can taper in so that the office at the bottom has the wider lease span. And actually at the very bottom, it has parking, which, cars don't give a damn of how far they are from a window. So the widest part is actually parking, then the office, and then the residential on top, and then there's an observation deck and a bar at the top. So if you ever go to Chicago and you want to go to the top of the building, there is the observation deck where you pay for tourists. Or you could go to the bar, that's the one story behind it, get a drink and get the same view. So just some travel tips for you guys if you ever visit Chicago. Anyway, so this is the ultimate sort of marriage of the structure and the architecture. And all of the perimeter, all of the lateral system is the perimeter. this is how it looks like in plan. So the taper is over one of the modules. The rest of the columns are straight. And then this is the floor plan. This is the columns here in the middle are just to hold the floor to reduce the span, and all of the structural, the lateral system is on the perimeter. And then there's a pool and residential parts. This is it going up. And another key thing that's, again, a theme that repeats a lot is what you do at the connections. So we can come up with all these optimized geometries to reduce the size of the elements. But in order to gain all of the savings and all of the economy, you have to really think about how things fit together. And very often it's the connections that really govern a lot of the sizing and so we think a lot about how things fit together. For example, here, the diagonals are actually rotated 90 degrees from what you would expect in order to make the connection as small as possible and to gather these savings. And there was when we first proposed this as a very efficient structural system, there was a big sort of trepidation or uncertainty about the diagonals, like who would want an apartment with the diagonal going through it. And in fact, if you look these days, the apartments with the diagonal sell for more than the apartments without it. So it was really embraced by everybody, and it's a big success. Another thing is this is the first building that was analyzed by computer. And then here's Fazla Khan with the IBM, some computer in the 1960s that there wasn't any computers in the office. So they did a partnership with the University of Chicago to use their computer. And the computing power was so small that they couldn't model the whole building. So they had to model only a quarter of it and use the end conditions to simulate the full behavior of the full building. So we've kind of been trying to introduce computational design from the very, very beginning. And here is the building as it stands today. Another sort of next step was in the 90s, and this is another really important building, is the Jin Mao. It's the first super tall building outside of the United States. Besides the John Hancock, it's the first sort of mixed-use tall building. And it really changed a lot of the building codes in China, and a lot of the buildings that are built, this giant construction boom in China, a lot of the codes and the construction methods were first developed on this tower. This is, again, a mixed use. It's got an office and a hotel on top of it, with the residential bit on the very, with an observation deck at the very top. And here, again, it's a new theme on this idea. Instead of having a bunch of closed columns on the perimeter, they put all of the lateral system in these 8 mega columns, so bunched it all together. Again, they're as far away as possible in order to make the building as stable as possible. And then there's the core on the inside. And then we have these 2 small, on each corner, there's 2 small gravity columns that are just picking up the corner. They're not part of the resisting the wind loads. And then the cool thing is that as you go up at the top, you no longer need all the office elevators and a lot of the other stuff. And so they actually hollowed up the middle for a pretty grand lobby inside. And then this is, when I was a student a long time ago, I got to visit it. So this is me hugging one of these mega columns. You can see the size of it down at the ground level in the lobby. And the trick of it is they have to be all connected from side to side. And so we do all these drawings and computer stuff, but sometimes it's really easy. Best is to just take your kids' play toys and build a model. So this is a model of the outrigger truss that connects the one side of the building to the other. And then this is the actual structural drawing of it. I kind of like this drawing as just, it's a technical drawing, but it's very aesthetic as well, I think. You see, it has all the connections, all the member sizes, all laid out of how it actually fits in the building. So this is, one side is the mega column and the other side is the core. And then this is what it looks like in real life. This is just to give you a sense of scale of what these elements look like. So this is the 2 mega columns and the core. This is the typical office plan, again, on the perimeter with I guess these are the local elevators that stop at this floor, and then all the other ones that bypass. This is another cool trick is whenever the elevators are just going by, we usually put the toilets and service rooms in between them. And then when they switch to this being the lobby, then the toilets would move here and things like that. So there's a lot of this, as I said, it's a big 3D puzzle with a lot of trickery of trying to utilize all the space. And then in the hotel rooms, you get the big open space in the middle. So this is a 30-story atrium between the 50-some floors and the 80-some floors. And actually, a lot of these super tall buildings going up in China and Korea. This one's in Shenzhen, in Seoul. This one's in Beijing, and this one's in Shanghai. They're all sort of structurally and are, you know, variations on the Jin Mao building. They have some core with some mega columns and some trusses connecting them all together. I should ask, do you want to ask questions throughout or at the end, or I can keep talking? I'll keep talking. Okay, so this is finally, we're getting to the new stuff now. This is one that I think just opened, we're supposed to open right before the pandemic. So I don't know if they've actually opened it yet or not. This is in Shenzhen. And the really innovative one is actually the Tower 1. This one's 400 and some or almost 400 meters. This is more conventional. It's 300 meters tall, so it's still not a joke building, but I'm mostly going to be talking about the taller of the two. And it's mostly an office building with a small hotel and then a restaurant and again an observation deck at the very top. And here, just like Jin Mao, we have 2 mega columns on each side and a big core, except that we wanted to have no other structural columns to get rid of these corner ones because there's a lot of good views around. So we wanted to just minimize it to only the 2 mega columns. And in a typical office building, you have these sort of corridor for if you have more than one tenant on a floor, and that makes the span between the facade and the actual core wall bigger. So we wanted to reduce this in order to reduce the load on the perimeter in order to minimize the structure and not have gravity columns. So we actually ran the common corridor through the core. And that way we ensured that you could have one tenant or 2 tenants or 4 tenants all on the same floor. So the client has flexibility in the future. And we actually sized the mega columns to be the depth of a typical office in China. In China, they do a lot of enclosed offices. In Europe and North America, we usually have more open office conditions. And the typical facade mullion is 1.5 meters. So we made the column 1.5 meters. And then the typical planning for an office is around 4.5 meters. The interior layouts, they usually work in 1.5 meter modules. And so if we size the column, so if you actually do fill out an office with offices, as you're walking down this corridor, the columns will completely disappear. They'll be just in the wall of all the rest of the offices. But if you do want to have an open space, then we want it to be as clear as possible. And in fact, to emphasize this, for this building, we took the typical window facade module of 1.5 meters and doubled it. So we have extra wide facade modules, again, to maximize this views out. So this is the goal that we had architecturally. And the structural system we came up with is this called ladder core. So if you take one ladder, it's kind of soft in one direction and easy to twist, but really rigid in the other. And if you put 4 ladders together, they're still soft to twist, but they're really rigid in 2 directions. And if you combine them with a tube core, then you have a pretty robust system that's rigid in all all ways. So it's rigid in both translation and in twist and torsion. And so this is our structural system. Instead of having these big outriggers and belt trusses, we have the core and we have the mega columns, and they're connected on every level. There's still some belt trusses along the perimeter. And in order to get rid of the other gravity columns, what we did is we decided to put the columns in, which is important to line up with the core, and then cantilever out the side. So this is kind of like we call it a balanced cantilever. And actually the cantilever on either side helps keep the forces in the big central span free. So every floor has I think it's 26 meters from face to face that are absolutely completely clear of columns. So it's pretty impressive span. This helps also control the gravity loads, so there's no uplift. The building is not trying to pull out of the ground. In order to make this work, again, this is again a 3D puzzle. We had to coordinate closely with the mechanical systems that, as I said, there's these air handling units on every floor, and they have to come out and circulate and make sure that air is delivered to every bit of the building. And so we kind of tightly coordinated how it happens in section between the core and the mega columns. And also, if this is a sort of an elevation drawn on a typical floor, you're looking basically at the face of the core. And so you have the entry to the elevators, and then one of these is the exit to the fire stairs and blah, blah, blah. And then you have the typical beams spanning between the core and the facade, and we coordinated all of the openings of all this stuff coming out of the core to fit in between the beams, all to make the ceiling sandwich as small as possible. So that's always sort of a big challenge also. And then structurally, the biggest challenge is these link beams, basically the steps in the ladder in the analogy that connect to the mega columns to the core. And so there's a lot of steel embedded in it. And so this is because this is a brand new system that's never been done. We modeled everything in 3D and actually built a finite element model where we modeled the steel, the rebar, and the concrete, and applied forces, and then make sure it performed well in each of the different earthquake and wind situations for the Chinese code. And so this is the structural system. There's the core, steel, mega columns. This is what the steel looks like inside the mega columns down at ground level.
I do have a question.
Yep.
So I understand that you have the freedom kind of to use this 26 meters without a column.
Yep.
But do you also have like an advantage to build higher? One question, and another one is, how's the comparison? So how much material do you use in comparison to the earlier method?
Ooh, that is a really good question. So the first one is we actually, if you notice, there's actually a double beam. So there's two of them in order to keep the depth as small as possible. And they are deeper than the small gravity beams that span to each floor. Actually, I think I have a picture. Oh, there you go. It's the very next slide. So this is it under construction. So we keep the small gravity beams that just span from here to here as small as possible. And then the big beams that span all the way across, they're actually part of the lateral system too. And it's a little bit of a peculiarity of the Chinese construction code, why they're so deep. They actually don't need to be so deep if this was built in Europe or the US. But anyway, and so all of the mechanical systems are in this, raised up zone. You can see the holes coming out. And so the goal is to maximize the floor to floor height. Is that what you're asking, right? So that's how we achieve that. I don't have the exact numbers for this building, but that is an important thing that we tracked about the relative savings in materials. And so this one, I don't know if it's more efficient than the Jin Mao, but that partly is because the code has changed a little bit in the things. But having this idea to the balanced cantilever, it reduces the size and the material in these buildings. So it's kind of managing where the load goes in order to make sure we minimize all of the material use. Oh, here's an example. Here's all of the mechanical systems then fit in. So the bottom of this beam lines up with the bottom of the duct, and you have a uniform floor. This is the facade going up. And then this is one of the finished floors of the 2 mega columns, and then the uniform ceiling below it. We didn't have anything to do with the ceiling they chose, but that's like usually every tenant fits that out themselves. And here's the corner again. You only see mullions, no gravity columns whatsoever. And here's the finished building. Another thing that we've been looking at recently is in this theme of optimizing geometry it actually got inspired by this obscure paper by this Australian engineer called Mitchell, who in 1904 wrote this short paper. This is, I think, half of the paper. And I don't pretend to understand every word of it, but he started with Maxwell, right, who's the famous physicist who is most famous for describing light and electromagnetism, but he also wrote some important papers in engineering. And he came up with these forms for the most efficient structure. So this is, if you have a cantilever, so it's supported here at B, and you have one force, if you have complete freedom to draw elements anywhere you want, if you follow the stress trajectories of what it wants to be, this is the type of truss that you would build for the most efficient way to support a cantilever. This is basically for a bridge, a beam that's supported on two sides with a force in the middle. And using our tools, different form finding tools, we've actually been finding this to be true in many different ways. So if you start with a design space, so you have a support here, and you just kind of do this random rectangle, and you put a load here, and you ask the program, how would the load get from the point it's applied to the support? And this is one of our tools. This one basically draws a bunch of elements and then runs iterations, and the ones that are not used get removed, and the ones that are used more get reinforced. And this shape emerges as the most efficient shape. This is another tool with a different mathematics behind it, and again, it converges to the same type of shape. And so we've been intrigued for this for 15 years or so around the office. This all started by, not part of any project, just people being curious, exploring. And so if you try to take this and apply it to a tall building, and it's kind of fixed at the ground, and you have a wind load on the side, if you run it again with several different, you get these patterns that emerge, and it kind of makes sense, right? That the top of the building wants to be more horizontal, where it's more sheer. Towards the bottom of the building, it's more bending, so you want it to be things to be more vertical. And so we've been playing around with this form, in different types of tall buildings. It's really sort of the next step after the John Hancock brace. This was in the 60s, where this geometry was already kind of very complicated by the type of drawing and engineering they had. And nowadays, you want to approach something like this. Obviously, a tall building like this, you can't really build all this curvy shapes and stuff like that. But if you start with a John Hancock, this is sort of a competition that we did, which would be the next iteration. And then this is a building that we actually managed to get constructed recently. So this is not a super tall, it's a mid-rise building in Sydney. Here's the Opera House and the bridge. So it's across from the typical downtown. And then, this is our first, we're calling it the high-waisted brace, because it using this analysis, it is really more efficient if you, oops. Well, that's not cool. Sorry about that. Okay, let me restart this. I think one of the animations booked out. So the Sydney building is it's an office building that has it's mid-rise. It has the core on one side, but let me get the. Okay, here we go. Ah, can you see? Okay, excellent. So this is the typical floor plan. It's pretty short, so the core is actually put on one side, and the brace is bracing the other side to balance the rigidity of the core on the open side. And we're using the same idea here of the balanced cantilever. So if you take a beam and you support it, you can the cantilevers on either side of it actually help reduce the forces in the middle. And if you take the bending diagram and you shape the beam like that, you actually get these pockets there. Again, you could hide the mechanical systems and get a bigger floor to floor. So this is what it looks like in real life. So you have the beams going through, and the slab spans between beams in the other direction. And in these pockets, which is material that you don't need for structure, so you're taking it out, you're saving the concrete, and you could use the pocket to run your ducts through it, and then reduce the sandwich of the structure. And then because of the cantilever, again, the perimeter has no columns, so the view out to downtown is column free on the upper levels. And then this is the high-waisted brace with the the more optimal geometry for the lateral support, rather than doing the straight through and through X. And again, the same theme. We can get this more optimal geometry, but really to get the savings and the constructability, we have to really pay attention of how the elements are connected on site. So this is a steel brace going to a concrete column, so how it goes into the column, and then how the forces in the brace resolve and pass through each other. So we had several different ideas of whether you connect them vertically or horizontally. And everything we work out in 3D before we actually, get it built. So here are the embedded things in the concrete, and the braces coming in with the node connection in the final building. So this is again a brand new version of the brace frame. I'd have to talk about Burj Khalifa too. It's currently the world's tallest building, and this is a building that's couldn't be built almost anywhere else. It's again a brand new structural system that's never been done before. It's this one I don't think would be as repeated as the Jin Mao and the John Hancock, because it's pretty specific. The plan of it is both inspired by local flowers and traditional geometries. But it's really also governed by the planning as well. So this is almost entirely a residential building. It's got a hotel at the bottom. Most of it is apartments. It has near the top something they're calling boutique offices, which are basically these really tiny offices, which I don't think would fly anywhere else in the world. But the three-way shape is governed by the program and by the structure working together. So from a program point of view, when you're selling high-end hotel residential and hotel elements, you kind of, again, you want views and access to sunlight, but you also don't want to be looking into your neighbors. So if you've all studied the Plan Voisin by Corbusier, right? These cruciform tall towers. When you have a four legs at a right angle, you're basically looking into your neighbor's apartment, which is not as desirable. So if you have 3 at this angle, you're really not seeing your into your neighbor's apartments. And structurally, it works very well. Again, it's the 3-legged stool is more statically determinant and more efficient than a 4-legged structure. And so in order to make this work, there's a central core that's a hexagon this time, that has all the elevators and mechanical shafts. And then going out, there's every wall is literally a structural wall. So we call this a buttressed core. So it's like a, Stefan's dome. It's buttressing the flying buttresses, buttressing the dome. And we call it the buttress core. And every element that you see here, every vertical wall is a structural wall that's buttressing or bracing the central core. And you can see it in the architectural plan, right? In between each of the rooms, there's these thick walls, and it works perfectly fine for a residential building, right? Also, as the pedals step in, the last pedal, which is open, has the columns. So the columns from one level line up with the walls below, so there's no transfers. Everything lines up vertically through and through. And this is going back a little bit to the fact that these buildings are governed by wind. The geometry of this building was really shaped by the wind engineering, and it's in this case, or in most cases for super tall buildings, it's not really the strength of the building that governs; it's the serviceability. It means the habitability, the comfort inside. So it's how much the building can deflect, and then how much you feel it inside. And there's different criteria for office or residential. For example, in an office building, while you're sitting at a desk and looking at a monitor, you can, it takes a lot more acceleration to make you notice it. But if you're lying in bed or eating at home, it takes a lot less acceleration. So a residential building has a lot more strict criteria for how much it could deflect and how much it could shake and accelerate in the wind. And so, sorry about that. I redid these slides at the last minute. So on Burj Khalifa, we did a very, very, very detailed and sophisticated wind engineering effort, and in coordination with the structure and the architecture. So the exact sequence of the steps and the exact layout of the building was all governed by the wind engineering. And these are all the different studies that were done on it. There's I won't get into it too much, but there's 2 different types of wind tunnel tests you could do. And almost all buildings are designed using this, which is called a force balance, which is, costs $20,000 to $30,000 to run. A more sophisticated one costs, $100,000 to $200,000 just for the wind tunnel test, and this is what was done on Burj Khalifa. And here, one freedom that we had is how to orient the building, because it was a big open site. You'd never be able to do this in Vienna or in New York or anywhere else. So we actually pointed the building so it points into the prevailing winds. So that was the first step. And then the second step is this effort in confusing the wind. How do you get the steps to be, and what's the best geometry of the steps in to make it work? So, you always start with some initial guess. So they started with initial guess. And if you take this as 100%, as they were, advancing the design, you could take the same load and the same forces by changing the geometry. You could actually reduce the base moment and the accelerations. And so this is the final scheme, has 3/4 of the forces in the original guess that was not optimized to respond to the wind. And here are some of the models that were tested. There was actually a version of it that was taller than was actually built. That even had even less load, even though it was taller. So this is this marriage, this idea of architecture and engineering working together to make a better, more efficient building that has less material in it. And here's the final thing. So the final story I'll tell you is one about, I guess, the future. So, and the last challenge. So we in many places in the world, in New York especially, and in most European cities, we've kind of run out of space of where to build. And a lot of our cities have these big train infrastructures left over from the 19th century that are in the heart of the city, and they're the where everybody comes in and commutes, right, in public transportation. And so these are the sort of the last pieces of land left to build on, and they're very fortuitous, right? Because this is the usually all the new subway lines meet there, so this is where all the people are. So if you can use the space and build above these train stations, is really the last bit of where to build. And you guys have that in Vienna, right? Mitte, or I don't know, train station used to be a train station that looked like this. And now you have a skyscraper and a mall and a bunch of other stuff on top of it. So you have an example of what I'm talking about right there, right next to you. And we've done it several times. This is in London. This is Exchange House. This is back in the 80s. And the building is entirely spanning over the train tracks of Liverpool Station. So here's now the station has a new building on top of it, but this is when it was constructed. So you have the train tracks running here, and the building is basically a big bridge spanning over from one side to the other. Just across the street from that, we recently built Broadgate Tower, and it's the same idea. Actually, SOM's London offices are in this floor right here, right where the braces come in. And this here's the Exchange House in the back. You could see it, and then this is Broadgate. This one, because the condition of the train tracks is slightly different, the geometry is a little bit different. But again, the building is spanning over the train tracks on a piece of land that was unused. But the final story is here in New York, and this is the west side of Manhattan. And these are two big developments that are going up still up on the west side. And this is really a piece of big train infrastructure that started getting built in the late 1800s. So all the trains down from Florida and Washington, D.C. come up through New Jersey, cross under the Hudson River, go under Manhattan and out the East River, and then up to Boston. And so this is the west side of Manhattan where the trains are. So this is Madison Square Garden, a big arena that's built over the trains. And then these are the two developments that we've been working on. There's actually a big old post office that's now getting converted into a train station, and a big office level that we're involved in as well. So we kind of, as SOM, we have a bit of each of these three big developments. And this is what the trains look like below. So this is 2 city blocks, and then this is the main platform where everybody gets in and off is here underneath Penn Station. And then the train tracks narrowed down between 9th and 10th Avenue, which is one development. And then they kind of splay out into a big parking yard, which is called Hudson Yards. And then only 2 of them are actually the tunnel going out to New Jersey. And this is a little bit of history. This was the Pennsylvania station that was built above where Madison Square Garden is now. And when they demolished this in the 60s, it really sparked the preservation movement in the United States. So it's connected to a lot of things, this site. But this is how the train tracks were built. This is in a picture from 1905 or so. You can see the steam locomotive when they were building the sites. This is the Penn Station going up. This is one of the avenues. And one of our sites is right here. And so this is what this looked like. There was only one building built in the 60s, but basically for 100 years, this is in the center of one of the most densely populated areas on the planet. There was this giant piece of infrastructure that was sitting there unused. There's a big hole in the ground. And we've done 3 tall buildings. So each of them is really governed by how they sit on the tracks. And each of them is around 300 meters tall. So the one is Hudson Yards, 35 Hudson Yards, where we sort of took an approach of aligning all of the structure and all of the architecture to match the cadence of the tracks below. Another one is 2 Manhattan West, where it's a big jumble of tracks down there. So here we kind of had to put structure wherever we could. And then 1 Manhattan West is the one building that I've been most involved with for the last 6 years. Is here we actually had an opportunity to avoid the tracks altogether. So the building steps in. So this is 35 Hudson Yards. Sorry. And you can see the building sits on the tracks below. This is mostly a residential and a hotel building. So this is the parking yard, and this is where our structure sits. There's a bunch of other buildings here by other architects and engineers, and they all sort of have a little bit of solid ground to come down on. This one is entirely over train tracks. And so what we did is every 3 train lines, there's a little bit of extra space. That's where we're putting our structure. And everything is lined up with these train tracks. So here's the groups of 3 with the structural elements in between it. And that really governed all of the architecture and all of the structure. Here's the first columns kind of coming in. You can see the trains below. And we had to start with steel in order to make it fit in between we had 2 feet, which is, you know, a little bit more than half a meter to go in between the trains. Because it's a residential building and then transitions into concrete above, and you can see as it steps in, everything has to be perfectly aligned with these dimensions that governed by the train tracks. Again, we did a lot of wind tunnel studies to shape the building. And above ground, there was a lot of different versions of it until we settled on this one. And this is the trick. In one direction, you could get bracing. In the other direction, it's this 300-meter tall tower. It just sits on a single-story moment frame. So the structural columns all line up, and then there's some gravity columns on the perimeter. And here's the final building. It just opened last year, right before the pandemic, and you can see it. It's this 300-meter tall tower with trains going through it fully. On 1 Manhattan West, it's an office building, so you can see it. It's just down the street, and here the tracks kind of narrow down. So our building is right above here in this area. And the first thing we did is actually, was done by another engineering group, is cover the train tracks with a big platform that it eventually would become a plaza between the 2 buildings. And this is what it is when the train tracks got covered up and we're starting to dig our hole for our building. But, you know, in order to get a proper wide office building, really it had to span from the street to over the last 2 tracks, and these tracks are you know, used 24 hours a day. So when we go there, which we had to do for the next building over here, really the train guys let you work, you know, every other night for like 2 hours between 2 a.m. and 3 a.m. you know, so it's really difficult to work around these train tracks. So on this building, we had the opportunity to take the columns that would be over the train tracks and bring them in. And the last piece of structure here is literally several centimeters away from the crash wall of the last track. But this would have created a very asymmetrical building, right? And it would have, you know, had a lot of tension here. So we did it is brought it in on the north side as well. And this is kind of like the essence of the structural system. This was a gym that my kids used to go to here in Astoria, and it's, you know, it's got the core and the main thing going straight down, and all the perimeter comes down through these arms stretched out to the ground. And it's a very narrow building. So the aspect ratio, if you take the height of the building and divide it by the structural width, it's 1:16. And you've probably, you know, there's a lot of these famous buildings nowadays going up that are 1:15, you know, very, very narrow and skinny, but most of them just go straight up. Ours actually kind of widens up. So it's both really narrow, but it also has these big sail area at the top. So it's a pretty challenging structural problem. And then we have a concrete core and a steel perimeter, and then it all transitions down here at the bottom. And that's part of the goal it's trying to resolve all of this strange geometry and all this gymnastics down at the ground level where you could build it easily. And then once you get to a certain height, it's very conventional, simple building that goes up really easily. Architecturally, we have 3 of the sides go straight up, and then the east side kind of slopes out and slopes back in. And we actually use this to our advantage. So because the east side goes up and slopes back in, it's actually the least load on it, right? There's a lot more load going down the west side than the east side. And so as I said the story, all of the columns on the south had to come in because of the trains, and we brought the columns on the north in order to balance the south. But on the east, we didn't really have to do it. We did have solid rock to build on here, but we brought them in anyway in order to achieve this pretty dramatic lobby down below. So the south comes in, the north comes in, and by bringing these relatively lightly loaded columns, we can have this 70-story tower with, this is about 12 meters of absolutely clear column-free lobby down on ground level. This is an early rendering of it. Again, in order to make all this happen, we had to pay a lot of attention of how all the pieces are connected so that we can, optimize them and make them as constructible as possible. And there's a lot of trickery of how to get this big element down to fit inside the core and to minimize the spacing between the elevators. So again, the elevator has a big influence on the structure and the architecture. And we always start with, again, this theme of we have a lot of these tools, but we always start with sketches and draw it all out by hand. Then we model it in 3D. And then this is the forces going through the structural elements with all the loads from the building, all the different pieces. And then, so this is the 3D model. This is our sort of documentation and drawing of it. And then this is one of the pieces on site. And after looking at this piece for this particular one where 4 of them come in, was really complicated. We looked at it for 2 years on the screen, modeling it on the computer, and finally we got to go see it getting built up in Canada. It was pretty exciting. And then, we started seeing it and goofing around to model it. It could look like a spaceship or, old warship and things like that. And then I finally got to see it arrive in the streets in Manhattan. So it got brought into this big giant truck. This is a bus compared to this piece of steel. So I actually got together with a colleague and my dad, and we drove in the car and chased it down the street as it was, passing through the city. It was pretty crazy to see this giant piece of steel just driving down the city. And here's a video of it getting put up. Sorry if it's too loud. So this is sped up a little bit. You can see the scale of it. This is about 90 tons of steel just kind of hanging out and coming in. And then, so, again, the scale of some of these elements as they're getting put up. We also had the concrete core go through, so we model every single piece of rebar in 3 dimensions to make sure that it all fits and resolves all sorts of problems before they get on site. So here's our model. And here's all the rebar getting put in on site around this complicated steel. You have to, really play around with it. How do you fit it all in together in 3 dimensions? The trains are running 24 hours underneath this truck here. So the last piece of steel is right next to the last train track. And then the core coming up. And then the rest of the tower. Here it is getting constructed in the city. Here's the Empire State Building. In order to take full advantage of this big column-free perimeter, we spend a lot of time engineering the glass facade. So it's all glass fins, and they're made out of 5 pieces of glass. It's probably, I don't know if in the world, but definitely in North America, it's the longest fin that doesn't have a splice. You've seen a lot of these glass facades, trying to splice a piece of glass is pretty clunky looking. You need a lot of steel in order to, spread the stress. And so these are 12-meter long pieces. I think it was the longest we could get of uninterrupted. The phase glass, it has 3 joints, but that's pretty small. That's just a very thin silicone joint. So it's super transparent. Here's the corner bit of it. And here it is, the 70 stories of office space coming down to a completely glass perimeter. This is a night shot. This is from one of my colleagues has a friend in an apartment, so we went and got some nice photos of it from above. And one theme is that we have is that we model a lot of things, and here's the 3D model, here's the steel, and it's almost exactly the same. And then the rendering, what we promised the client, and then what we delivered at the end. And finally, I think I have a little bit more time. We're now working on the cousin of this tower, which is 2 Manhattan West on the other side. And this is the one where it's a really big mess of trains below it. So this is the outline of the tower above. And green is the only place where we could put structure. So you could see some of it is actually outside of the tower. And this is what was existing, all the train infrastructure that we had to, thread a needle through in order to build this building. So here we basically, it's not as neat as the other one, but basically we had to kind of transfer each column however best we could. And here on the north side, the perimeter is undercut. On the south side, it's kind of the opposite. The core is undercut. But we had the same strategy of doing all the complicated gymnastics down at ground where it could be easily built, and then a pretty simple building above. And for the facade here, the client wanted to sort of match the other one, but the way the site sloped, you actually get 15 or 16 meters high, which was too big for a single piece of glass. So on this one, we're doing a cable net. And in order to minimize the impact of it, we didn't want any of these big spider connections that were popular 10, 15 years ago. So we're kind of doing a very, very small connection that's all going to be tied. So instead of grabbing it like the big spider clips, we're having these little shelves that are hidden inside the cable. And then this is the 3D of that connection. So the client wanted to match the other tower, which had the really thin glass fins. And so here's a little bit of a animation. We have the anchors down below, the thin double cables, and then anchored up at the 4th floor behind in the ceilings. And so in closing, this was 6 years ago what the site looked like, and this is 2 years ago. There've been a couple more towers completed since then. But this is just beyond economics, trying to build and in places where were unbuildable before is really the idea, is to be as efficient as possible and to build as best as possible in order to, live in a world of limited resources. So that's all I have for you for today. I know maybe it was a little bit long, but there's several interesting stories I wanted to share.
Thanks a lot, Georgi. Super interesting. I'm sure you have much more to tell us.
Yeah, I have more stories, but that's probably enough.
Thank you also for giving us the big picture and the details to it. It was really interesting to see how you bridge the railroad. And let me ask the students if they have questions for you. Please go ahead.
I would have a question.
Go ahead.
So in the beginning, you mentioned that we are confronted with overpopulation, especially in the next 25 years. So considering that around 70% of the population will live in the cities, we need to get creative as architects and engineers. So I was wondering, because we are lacking the land to build, and you mentioned the train stations as new innovative solutions. Do you see other potentials as a train stations that we could use as potential sites to build?
That's a very good question. It's the rail infrastructure is the one that seems to be first. Even in smaller buildings, I'm working on another building in Boston, which is a 8-story university building, and that one's also over a train track. It seems like even if it's not in the super dense centers of the cities, even around the perimeter, I'm always dealing with trains. Another thing here in New York especially is along the waterfront, there used to be a lot of factories, even in downtown. And I know in Chicago, in London too, we have a lot of projects. So all the factories that used to be along the perimeter, now all of the city rivers like the Thames or Chicago River, and here the East River, the perimeter is getting turned into parks. And then very often what they do, I don't know about Europe, but here in New York, the city usually does a partnership where right next to, the very waterfront, you do a park, but then to pay for the park, inland, you let somebody develop a tower and then use the money from that to pay for the park. And so it seems to be a pretty good synergy. So you get a lot of tall towers along the waterfront, and the city gets a nice park on the waterfront, and then that's how you get to pay for it. And so, some of the people that live 2 or 3 blocks down the street usually sometimes complain, but that there's this big new tower. But before they had a abandoned factory. So I think replacing an abandoned factory on the waterfront with a waterfront park and a tall residential tower, I think is a very successful way to go in the future. So that's something that's going on in London and New York for sure, in Chicago, where we have projects.
Mm-hmm. Thank you.
There's a question in German though. You have to translate it for me on the chat.
Just yes, please.
Question too. In Vienna, we have the world's tallest wooden tower. Do you think wood could be a material for high-rise buildings too in future, or?
Ooh, that's a very, very, very good question. Yes, definitely. And we do have a research project, and we've published several papers taking sort of, not 100 stories, but a 30-story tower. We have a design, and we've been proposing it for several competitions. Let me see, I can even maybe, I'll stop sharing and I'll see if I can bring up some images of that. So there's a couple of challenges in that. First of all, it's kind of, right, it's new, so you have to prove it to people. There's in the US specifically, the building code doesn't allow you to use wood above 8 stories. And so most in North America, at least, most of the leadership in this is in Canada, where I think they recently built a 20-story thing. I think in Europe, there's several that are over 10 stories already. They're working on changing the US code to allow this, but I think it will take effect in the next couple of years. Not only for the vertical structure, so we have this proposal for a vertical tower, but we also trying to incorporate it very much for the horizontal structure. So to replace the concrete slab or the concrete and metal deck that spans between steel elements. And we've done some research with universities in order to validate some of the systems. So we're definitely exploring this idea of using, in the US, we call it CLT, a cross-laminated timber. I don't know what the term is in Europe, but both for the vertical structure and the horizontal structure. So I don't know if I'll be able to find the images real quick, but. Go ahead with the next question. I can look through this in the meantime.
I have two questions.
Mm-hmm.
The first one would be, you've mentioned the three forces before, the wind force, the seismic force, and the gravity force.
Mm-hmm.
I was, how would the earthquake, how would it impact the tall buildings, and what metals are good, I don't know, to prevent it, the collapse?
So that's a very good question also. And that one, actually, I can bring in the images pretty easily. I didn't include it because I wanted to keep short, but here's the seismic portion of the. Can you see the screen?
Yes.
So the way the seismic works is, right, it's the simple equation from high school physics, right? You have F equals ma. So you have some mass of your building, and the earth provides the acceleration, the A. Force equals mass times acceleration, right? I remember for this from physics class. And so the earth provides the acceleration, the building has some mass and it doesn't want to move. And so you have certain forces. And this is a graph of the forces in a seismic event, and it really it depends on the. Your building, and then this is the percentage of the acceleration of gravity. So percentage of the gravity force that you have to design for is a lateral force. And if you have a 1, 2 to 10-story building, they're usually here. So they're usually about 1 to 2 seconds of vibration of the building. Most tall buildings have a fundamental frequency that is much longer. So they're usually like 6 to 10 seconds. And so because their frequency is very different than the earthquakes, usually the forces in a tall building are much, much lower than what you would see in a short building. So in an earthquake event, the safest place to be is in a super tall tower, because really the earthquake kind of goes by it, and it doesn't really excite it, both because of its mass and because of its period. And so that's why when I said that tall buildings are almost never governed by seismic forces. It's only very peculiar places like Mexico City, which is sitting in a lake bed and has really crappy soil, and it's in the middle of the continent, so the wind loads are low, and then there everything is governed by wind forces, by seismic forces. Almost everywhere else in the world, for a tall building, it's all 100% governed by the wind. So yeah.
And the second question, you are also building above rail tracks. I was wondering, what about building above water? What is the opinion on that, and how would that be possible? Because I've seen examples in Copenhagen. So
yeah, and actually most of downtown Manhattan here, and the old World Trade Center, and now One World Trade Center, the new tower, they're all on reclaimed land. Usually, you kind of fill in the land, and you don't actually let water, slush underneath the tall buildings, because you usually have a basement and parking and things like that. So the way we do it is kind of dig down through the water. So that's very common. It's usually reclaiming the land though, but not building over the water. From deep, the foundations is a whole other long story of how you anchor these tall buildings to the ground. And in Manhattan here, we're super lucky. These buildings that I showed you, these 3 buildings, this crazy gymnastics that we're doing over the trains is only possible because we have incredibly hard rock right at the surface. So here you just kind of have to dust off whatever garbage is in the top and you can just put your building there. You know, we're designing another one in Indonesia and in Mexico also, where, you know, Jakarta, for example, is in a floodplain. And so they dug a test well 300 meters down and there was no rock. It's just like sand and silt and just stuff that's like just been deposited there. And so the foundation design there was very sophisticated and complicated. And we had to argue a lot with the geotech engineers back and forth. Same with Shanghai, all these big cities that are in the deltas of big rivers, the rock is, you know, far, far down. And so it gets a lot more complicated to do the foundations there. I don't know how it's in Vienna. You guys are right next to the Danube, so I assume the rock is not that close to the surface either. So yeah, we do, like, you know, when you put a foundation that's, you know, 100 meters down, that's below the bottom of any water. So usually kind of build a bathtub around it and go down.
Mm-hmm.
And you know, New York, Manhattan, the lower Manhattan, almost half of downtown is on reclaimed land that you've taken over from the bay. So that's very common.
Okay, thank you.
Cheers. I can't really pull up the thing about the wood tower. I do have this image of what I was talking about, the cross-laminated timber deck. So this was something we keep proposing, and we actually got one built recently in Switzerland, in Geneva for, oh, actually I can pull that up real quick, where it's the main structure is concrete, and then the slabs are the metal deck, or the wood. So that is something that's very, very nice, because then the building is, you know, not only using reusable materials, but because the wood sequesters the carbon, you can get a lot of benefit from actually, instead of the building releasing carbon, it stores carbon from the atmosphere.
Georgi, can I ask you a question in between?
Yeah.
You have talked a lot of the process and the change of the process towards optimization of building structures and historical developments and where you are now. Where do you think will we be in the next 10 years in terms of building optimization? And I would like to know what you think how the role of the architect or engineer will change.
Oof, that's a very philosophical question. I have several things I think that are going on. A lot of people are talking about 3D printing, which we're starting to experiment with on small scale. I don't think we're anywhere near 3D printing to the scale of what the buildings that I'm talking about, you know, a skyscraper and things like that. For a single story building, you know, there's some pretty successful things going on already. For now, for these big projects, it's really concrete and steel are the way to go. And as we're talking about, we're trying to introduce wood wherever possible. And it's catching on, and you know, the codes are catching up as well. The other long-term, I think, development that we've talked about is you know, artificial intelligence and using that for design, and we're already seeing it on the construction side. For example, in detailing, designing the steel connections for all these towers. So, you know, One Manhattan West, the tower has, you know, hundreds of thousands of connections, you know, and the number of bolts and things like that. And a lot of these are very prescriptive. So they used to be designed, you know, one at a time, but now we're seeing there's several companies that have popped up that basically can design all the connections in a couple of hours. It would take months for an engineer to do. That's for a very prescriptive thing, and so we're looking into that actively, actually, and using machine learning. Another project we had is a part of AI and machine learning that's pretty advanced is image recognition. So using surveys of the site to do construction administration and to monitor what goes on the site. Both in, so we had a project with timber, a new library that we built just recently, and it had some cracks in the timber. And so we used machine learning to help find them all from pictures people just took on site. So far, it's limited to analyzing images and analyzing stuff and doing simple repetitive design things. But we're one thing that people are thinking about is how as these tools get more powerful, how will they take on the design, and can you teach them to be creative too, or will they eventually be both technically fast and creative? And then where do the humans fit into that story? And so one way we're approaching it is we're trying to be the engineers and architects that are designing the algorithms that the tools will have, or designing the tools. So that's still a place for creativity. But that is something that is coming in the next 20, 30, 40 years. And, I think my job is safe until I retire as an engineer and an architect. But, you could be the one teaching the computers how to design, or be out of a job at some point in the future. So maybe that's too far out, but that's something people are talking about in our profession. So far, anything that's not creative and repetitive is the low-hanging fruit, and is already being picked up by the computers and the algorithms. So far, creativity seems to be a safe human-only place, but I don't know for how long.
Are the engineers and architects prepared, do you think, at the universities for this development?
I mean, I think the younger engineers coming in are better prepared than I was when I entered the work 20 years ago. A lot of these in-house tools, I help guide people on what we wanted to achieve, but I can't write them myself. So I think, and not everybody is prepared or interested in this type of stuff, but we're able to find people that are. I don't know how well universities prepare you for this. I can't tell you that, but we're a pretty small group, actually, in the structural engineering group at SOM. We do all these pretty fancy projects, but we're in the New York office. There are only 25 of us, and I've been pretty lucky to be able to hire some pretty bright people that want to come and work on these projects for us. I don't know if a lot of other big engineering and architecture firms are more into production, and you get put in and you do beam design or column design or toilet layout for 20 years, and they have this sort of compartmentalized way of structuring their work, where there's somebody that's doing one thing and they're really efficient in it, and they could charge less, but then then you churn out the same building over and over again. So I'm feel pretty lucky to be working in a place where we can do all sorts of creative stuff and pull it off. You're on mute.
Yes, we have time for one question. If you want to ask Georgi Petrov something about his talk.
I have another question. Mm-hmm. It's more a chatty one. but I am really used to really small offices. So wondering how it looks like working for or at SOM. The team sizes and the hierarchy and the dynamics and yeah, so.
Yeah, that's a good. So on, as I said, the structures group, we're actually much smaller. Like the companies like Arab and Torton Tomasetti and Lira that we compete against, they all have, you know, thousands of engineers. And we're along all the offices, London, Chicago, New York, San Francisco, we're 110 total structural engineers, and in each office is around 20 or 30, which is a pretty small group. On the architecture side, the New York office, I think we have around 200-ish or so. And then the groups vary from project to project. There is some specialization, but we're not very rigidly divided into studios. There's the young architects, engineers, we consciously try to give them varied experiences. On the architecture side, there's this a little bit of a divide at SOM between design and technical. So there's the people in charge of doing the renderings and the design, and then there's people making sure all the details work. And so there's a little bit of that divide on the architecture side at SOM. But overall, when you work on a team, it's depends on the project, but you know, 10, 15 people. So the teams are not these fast things. We do have some big projects where, you know, you get the team about 20 people to pull off an airport, for example, and things like that. And then there's some rigid like groups, you know, we have a team that sort of does mostly hospital type things, and then a team that does airports. But the young architects and engineers, we kind of move them around to get them exposed to different things. We also have a facade group. So we have like maybe 5 or 6 people that are sort of specialists in facades, and they're kind of like internal consultants. They work on many projects at a time. We don't engineer. Usually facades are what we call delegated design. You kind of bring the design to some intent, and then the contractor really works out all the details. But so we do have that. And then we have a urban planning group that we don't have any of them in New York. They're mostly in Chicago and San Francisco. We have a very big interiors group. They do, they're sort of a little bit more separated, but they do interior fit outs, not outside buildings. So, and we work with them quite a bit too. Sometimes we engineer stuff if they have some fancy stair that they're putting in some interior office, we engineer it with them. So it's not very terribly rigid inside, and it doesn't feel like a giant firm. Cool.
Thank you very much, Georgi. I have
Thank you.
to close